quickly. There will be a reception which will bring all the visitors to the Newton Institute and other people together. And this is to mark our start of the program and also to welcome everybody. So just a few words about Emmanuel Villermaux. Got his PhD in '93 in Grenoble, but it was through the Université Paris 6, Marie et Pierre Curie. And then he stayed for a while in Grenoble at what was then called Joseph Fouillet Université, and changed names several times since then. Eventually he got his habilitation there. And then in 2000, he tells me, 2000 plus minus one, he moved to Marseille, where he is a distinguished professor. He is an APS fellow, also fellow of Euromec. His interests are in deformable medium bodies, from fluids to solids, broadly understood, with particular penchant for droplets, especially droplets that disintegrate, and also for, more broadly, for fragmentation and mixing. And today he will tell us about morphodynamics of cohesive objects. Let's welcome him here.
Thank you. Nothing that has just been said is wrong. So it's, the police search was correct. Okay, morphodynamics of cohesive objects. This is a bold, probably too ambitious title, because as you'll see, I'll be talking about very simple things. But the merit of this title is that it is explicit. So morpho refers to shapes and forms, and I will be discussing shapes and forms. And dynamics, the idea will be to understand the shapes as a function of the dynamics which gives birth to them. And the essentially two examples I will be discussing involve cohesive objects, meaning that cohesion in the sense of internal attractive forces in the objects are involved in the overall dynamics. Okay, so the examples I remember the examples you have here are so this is a solid object window. This is the impacted window problem. If you throw a bullet on a window, it first deforms elastically, and then it cannot sustain the deformation, and the optimal shape which arises is this kind of a star-shaped pattern. So it's a form, it's a shape which results from a competition between deformation, inertia of the bullet, and the elastic response, its cohesion of the material. So that's an example. This is a similar example of an object which is torn. The celebrated example of the droplet impacting on a solid surface. Again, cohesion is due to surface tension in that case in the liquid, and because the droplet has impacted on the solid, there is a dismantling motion due to the inertia of the liquid that the surface tension of the liquid has to counteract to keep the liquid as a single body, but it does not succeed because from time to time there are droplets which are formed at the edge of the expanding sheet resulting from the impact. Okay, I will explain what this is. But if we look at least at these two examples there, you see that the shapes, the forms, result from a collection of singular objects, singular regions in the material. The tip of a fracture is a singular location concentrating the stress and the mechanical energy. These cuts I will describe between the ejected ligaments forming drops are also singular structures, and they organize, in some sense, the environment in which they live in order to give birth or to give rise to an overall shape. So there are many examples, of course, of this in nature. To start with, in the room where we are, which therefore was chosen appropriately for this seminar, the problem of the curtain. The curtain is a sheet of anything. There is graphene here, which is tightly folded at the beginning and then left evolving on its own without any further buckling forces. And the overall dynamics, if we may call this a dynamics because the process evolved in space, gives rise to a kind of coarsening process where larger and larger folds emerge. This is the same kind of phenomena I was describing before. The folds concentrate the mechanical energy through bending, and then they interact in order to give rise to larger and larger structures. So that's an example. Let me show you another example involving singular structures which evolve through an interaction between their neighbors and therefore shaping an overall front. This is a flame front. A front propagating in a mixture of propane and air. So as you know, probably flame front is naturally unstable. It does not remain flat. There is a fundamental instability which explains why the front needs to be distorted and presents these singular cusp structures oriented towards the burned gases. This is a Dario-Landau instability. And if we let the front evolve, you see that these cusps interact, merge, they get birth, they're constantly regenerated along the front, and they interact in order to give, at a given instant of time, a set of cells which are distributed in size. So if we integrate this in time to see the history, you see that indeed the evolution of this front separates larger sizes, larger cells in the vicinity of which you can find cells with different sizes, small, large, and that there is a dynamics of birth, coalescence, and therefore disparition of these cells, giving rise to a statistically well-defined object. Okay, so the two examples I've just shown don't involve cohesion per se. In order to address problems with cohesion, I like to go back to the work of Félix Savard. Félix Savard, who was before Darcy Thompson. He was not really a precursor of Darcy Thompson because his interests were different. But I like very much his seminal work because it was especially designed at understanding the consequences of cohesion, that is small-scale attraction between fluid particles, on the shapes in the macroscopic world. And to do that, he had thought about extremely simple and elegant experiments, one of which being the impact of a jet on a solid surface, very much like this is a continuous version of the one I was showing before, of the droplet impacting on a pillar. From this impact results a sheet, which is a modern view of what Savard had done, so-called now, and since then, a Savard sheet, which is an expanding liquid object ending at some point, depending on the impacting velocity of the jet, of the diameter of the jet, and at the border of which we find, well, precisely these singular structures, these nodes, forming cusps, defining cusps at the tip of which ligaments are expelled, which ultimately break up, forming forming droplets. So that's a comparison between a view with modern instruments, fast cameras, with the one which was imagined by Savard, who had his naked eyes to look at that. As you see, that's not too bad. I mean, the drawing is not too bad. These cusps, there are too many, and their shape is not exactly the good one. They're positively curved instead of negatively curved. But overall, Savard, who again had not the modern instruments we have, had the correct overall scenario. So there is these cusps, these nodes, between two nodes is defined a cusp, sit at a well-defined distance from the impacting point. A distance which is a function of the injection diameter of the jet and of a number which precisely measures and compares the intensity of the inertia of the liquid as it expands after the shock, after the impact, and the confinement surface tension pressure. Typically, this number is large, otherwise the liquid would simply not expand at all because it would be confined by surface tension. So by large, I mean typically a few hundreds. And these nodes sit at 4/5 radius, which is celebrated, at least here in Cambridge, because it is due to Taylor, G.I. Taylor. And the C stands for Kulik. So this is the radius which is attributed to Taylor and Kulik. Taylor, who was, it does not happen often, but he was on this issue wrong, or at least he made an omission. Taylor, who was also interested, of course, in the work of Savard, thought that the equilibrium between the inertia of the liquid and surface tension confinement would be at this location, which is a little bit larger than the one where we find these nodes. So I can explain to you this rapidly because it is very convenient home. Everything is very well organized. It's easy to pop up the blackboard. So we have the jet which is impacting on this solid. We are looking at the situation from above. And it is expanding like this. And it turns out that for reasons linked to mass conservation, the sheet gets thinner and thinner as larger radii are concerned. So if the sheet is thinner, there is something which increases, that is the Laplace pressure. It increases as the radius gets larger. And there is something which conversely is constant because the radial velocity is conserved. There is no loss, so the energy is conserved, the radial velocity is conserved, the kinetic energy is conserved by unit mass. There is something which is constant, that is the incident momentum. So since this decays, there must be a radius where these two terms will equilibrate. And that's the famous Taylor-Kulik radius. So if we blow up what Taylor had in mind at the extremity of the sheet, you see that we have this sheet which is spinning, something which happens here where precisely inertial forces and surface tension forces equilibrate. And this is where this equilibrium is reached. However, what is missing in this piece of reasoning is mass conservation. This is momentum conservation, force conservation, but there is no mass conservation. We don't know what to do with the liquid which is accumulating in this rim. It is there, it sits there. That's precisely because Taylor had not the exact picture. The picture is not if I look at this from above, a smooth disk where the equilibrium is reached there, it is in fact a collection of these cusps whose foot, these nodes, are located a little bit before, or for radii, a little bit smaller than the one where the Taylor-Cubic equilibrium is reached, and where both momentum and mass conservation is enforced, or is complied, precisely because there is some room for the liquid to be evacuated. And after that, it is evacuated at the top of these structures. So I needed to mention this in Cambridge. You will forgive me. Okay, so let's go back. Of course, this is an instantaneous view, but if we look at the situation as it is not in real time, it is slow time, of course. This is what happens to these nodes and to these cusps separated by or bordered by these nodes. So you see, the nodes are traveling along the sheet. So the liquid is coming from here. You recognize the droplets which are expelled from the tip of the ligaments, and clearly there is a dynamics associated with the existence of these objects. Very rarely they stay stationary along the sheet. It happens for a short while, but typically they are, so this one, for instance, is probably close to be of being stationary because it is a little bit, it is so close to symmetrical. But that one is clearly going in this direction because the pressure recoil associated with the jet from its left is much larger than the pressure recoil from the one on the right. So clearly there is a net force pulling this guy on the right. And our objective is to understand the overall shape of this cusp, at least their distribution of sizes, as a function of what we can understand from the dynamics of the nodes.
So from the picture, we don't see this liquid sheet at all.
No, it was. You want me to explain where it is?
Yeah.
That was relatively, well, that's, as you know, it is always obvious to somebody who knows. So the sheet is here.
Okay.
The sheet is here because the droplets are expelled in this direction. So you could tell, if you had been thinking a little bit. But I agree, I could have, the movie is not absolutely self-explanatory.
Too transparent.
It is too transparent. No, it's the projector of.
The camera.
No, but I agree. I mean, this thank you for. But you know, I have seen I have shown the instantaneous pictures, and the cusps were organized like this with the. Good. So the same criticism is here. Huh? The sheet is here, and this is. Okay, so that's a stationary cusp. It happens once in a while, very seldomly, but it happens. And again, elementary fluid mechanics, along the mechanism I was describing before, qualitatively, says or explains that the angle of ejection of the two side jets has to be such that their tangent is 1/2. And because of the recoil pressure associated with this outcoming jet from the node, the position of the node is a little bit before the Taylor-Cubic radius. So that's the stationary node. But typically, as we have seen, these nodes are not stationary, they are moving. And they are moving for a very simple reason. If a node is in between cells of different sizes, a large one and a small one, well, geometrically, it is obvious that this one will present a smaller angle than this one. So the ejection angle of the side jets being different, there will be a net force oriented in the direction opposite to the weakest angle. obvious reason, pressure recovery. And again, simple geometrical arguments provide the drift velocity of the node as a function of the contrast between the two ejection angles. If these are close to the equilibrium angle, plus or minus a small correcting angle, then the velocity is simply given by the tangent of this shift from the pure equilibrium, u being the incoming velocity of the liquid. All right. So this is, I mean, detailed fluid mechanics in some sense, explaining the dynamics of these cusps. So this is basically what you have seen before. We see a sequence showing how this node travels in the direction, it travels so that the smallest cell in the vicinity of a larger one gets smaller and smaller to disappear completely and to give rise to a larger cell whose value in size is simply the sum of the two initial sizes, because the central node has disappeared. And yes, the study of a large collection of these nodes shows that indeed the velocity is positive when epsilon is positive and negative when epsilon is negative, with some noise over the overall expected trend. All right. An extremely important point here is at the same time absolutely obvious and simple, but important. The interaction between these cells is additive, simply because this node essentially disappears. The small cell decays in size at the expense of a large one. So if we start with two neighboring cells, the final size after complete interaction is simply the size of the initial cells in the vicinity of each other. It's a sum. And of course, the process takes some time. It takes basically the time for the node to travel on the distance given by the size of the smallest cell, the one which disappears, at the velocity v. And elementary computations show that this time is essentially given by the average size cell size divided by the incoming liquid velocity, so this is the overall time scale, times a geometrical factor, which says that when, by chance, the size of the cell has the mean size cells, that is, when the couple of two cells is identical in size, that is, when the node sits exactly in between the final large cell, well, the interaction time will be infinite. And if it's not the case, the merging time is smaller when the size S2 is small. And precisely, since there is a distribution, a hierarchy of these aggregation times, the smallest being those where the smallest sizes occur, an aggregation criterion explaining that in an experiment it will not be possible to see a cell because it disappears too fast in a large collection of cell sizes, is that the aggregation time, the critical size for aggregation, should be smaller than the typical aggregation time, S being the average cell size, and sigma being the root mean square of the cell sizes distribution. That's an aggregation criterion. The fact that the interaction rule between adjacent cells is additive implies that the cell size distribution has to be stable by self-convolution. So this is the equivalent in distribution space of the interaction rule in the variable space. So these are so it's a family of gamma distributions with a single parameter which has to be related to the dynamics, the microscopic dynamics of the interaction itself, and this is where we use our merging criteria. So this is the expression of the merging criterion once the distribution is known in shape, the gamma distribution. And the merging criterion explains is satisfied when the order of the gamma distribution, so this parameter nu, is larger than 4. So just to show you what we are talking about, so 1x is the cell size divided by the average cell size. X. Nu equal 1 is the exponential. Larger orders give rise to distributions which are like that, so that would be nu equal 3, for instance. Nu equal 4 is something like that. And very large values of nu point the distribution around the mean like a Dirac delta. So what does it mean that nu has to be larger than some value? We have found 4 using our criterion. Well, if nu is smaller than 4, this means that we have a too broad distribution presenting too many cell sizes, small cell sizes, and the small cell sizes, we've seen that they disappear very fast. So it is not acceptable to have small cell sizes or too small cell sizes in too large proportion, precisely because they have no time to live. And this is exactly what our criterion expresses. The order has to be larger. Now, why is nu equal 4 the one which is expected? Well, if the distribution is too narrow, since cell sizes are regenerated permanently because of random fluctuations, the distribution which is too big around the mean is not acceptable as well, because it is fed on this side by larger and larger sizes due to nucleation. So this is indeed nu equal 4, which is expected, and this is what is measured indeed, including, so this is the exponential tail characteristic of the gamma distribution, which is emphasized on the big graph, but the algebraic behavior at small sizes is recovered as well. All right. So, and this is nu equal 4, indeed. So, a preliminary conclusion here in the Darcy-Thompson mood is that, well, we have characterized the, I mean, statistically at least, the shape of an object, collection of cells bordering a liquid sheet, by identifying the process which gives rise to them. And since we have documented the kinematics of the process, we were able to set the exact shape of the distribution, this nu equal 4 mechanism. And it's an interesting instance where it is in fact deterministic fluid mechanics at the microscopic level, the motion of these nodes, which allows to understand the shape of the distribution. And that was a little bit the ambition of Darcy-Thompson, I think, understanding the detailed mechanics of complex objects. It was one of the ambitions. I'm trying to relate what I'm saying to I do my best. Okay, so let me give you another experimental example exactly in the same line of thought. So we have looked at a jet which was forced to expand because of an impact on the solid surface, but the jet is a continuous stream of liquid. We could exactly in the same spirit do the impulse response of this problem by using an object which is a cohesive object, again, but a one-dimensional object which is violently expanded. So you will understand. We are using the one-dimensional object is in fact a necklace of atoms, let's say, beads, magnets, in the present case. They sit on a cone, and when the cone is falling by its own weight, and when the cone when it hits the floor, the necklace is expanded. So that's pretty much the same idea as previously, except that we are using a one-dimensional object instead. So, seen from above. Okay, so seen from above, you see what happens, and what you see precisely are things which are very similar to those we have seen before. You see that at early time, the necklace is practically completely atomized. The beads are separated, that they coalesce, and they coalesce faster when they belong to a cluster of beads, which is smaller, of course, we'll describe this, to form larger and larger aggregates. So that's what is called an inverse cascade. So that was the image I was showing before. The forced radial expansion produces extremely short fragments at short time, but these fragments, as they expand, remember that they were linked to their neighbors and aggregate with them up to a time, or equivalently a radius, so this is expanding in space, where the clusters of aggregated beads are so large and so distant to each other that they can't interact anymore. And then at that instant of time, the distribution of the sizes is fully set and will not evolve anymore. Of course, if the initial expansion rate is larger, the everything being constant and the cohesion between the particles, that is the adhesion force between the particles being the same as in that case, the number of fragments is smaller. The typical size of the fragments is smaller, precisely because inertia is more intense in that case than in that case. Of course, exactly as in the previous case with the liquid sheet, since there is an attractive force, so I mentioned that we are talking about magnets, so this is dipole-dipole interaction. Dipole-dipole interaction involves a force which is decaying like the force power of the distance between the objects. So it's a long-range interaction, but it's an interaction which goes to zero relatively rapidly anyway. So this is for the cohesion in that case, and there is the equivalent of the Weber number, of the same kind as we were describing before, precisely as the ratio between the expansion velocity initially, rho being the density of the beads, and the adhesion force. And yes, when the Weber number is larger, the final fragments are smaller than when it is smaller.
Is the adhesion force only between nearest neighbors? Or?
So that's a very good point. Yes, with what I'm writing here is I'm just counting the influence of the ending
Yes.
beads on the attraction. However, you can resum, you can do the sum, and you will realize that the predominance of the edge interaction is extraordinarily strong. So.
Mu not magnetic moment, correct?
What do you mean? Yeah.
Of the mu magnetic moment of the individual bead.
Exactly. So the magnetization of.
But your wave number here is extremely small if someone comes from the fluid mechanics point.
No, that's true. It has to be smaller than 1. You'll understand why. But it's what matters is not so much the numbers. What matters is the fact that you change the phenomenon response as you expect.
I think M is the magnetic moment, isn't it?
Yeah. And mu is the
zero
permeability.
Conventional mu zero in magnetism.
Oh, I can, yeah.
Okay.
Yep.
Temporal evolution of this assembly of beads. So initially, here we have the average fragment size versus time. Here we have the expansion velocity of the necklace, or fragmented necklace, as a function of time. So as you can see, the number of beads per cluster is initially small, 2 or 3. This is consistent with the fact that the necklace looks completely atomized initially. And this number increases as a function of time, and it increases up to larger values when the Weber number is smaller, of course. This is the sign of the aggregation phenomena we've seen. And at the same time, the velocity, the expansion velocity decays. So it would not decay if the fragments were isolated. They would have a ballistic motion. It's not a ballistic motion, it's a slowed down motion, which is consistent with the fact that initially the beads are sitting on a curved profile, on a curved surface, and that the attraction between with the neighboring clusters gives rise to a net slowing force. This is a sign of surface tension in some sense, or of collision. So there is a force which prevents the ballistic motion of the fragments, hence explaining why the velocity decays. It decays up to a point where it does not decay anymore, precisely because the fragments are too large, so too massive, and too distant from each other. The velocity decays, but the radius r increases. They are too distant, and the population of fragment does not evolve anymore at that time. Okay, so this is the overall description of the inverse cascade, if you like. And as before, we are interested in describing the overall assembly of the fragments, their size distribution, cluster size distribution. N refers to the number of beads per cluster. So what do we see? We see that at a short time, this is for the short time. Sorry. Okay. At short time, the distribution is peaked around a few units. It is not peaked, it is at least more peaked than at later times, where the distribution is broader, as the mean of beads per cluster increases. So there are two trends there. The mean increases, but the width of the distribution increases as well. Now, if we look at the distribution not in number, but in number seen at the scale of the current mean, now all the distribution collapse on the same rescale curve, which happens to be well fitted by a gamma distribution of order 8 in that case. So that's the overall thing. This is fragment trajectory. I could not. This is not. This is just to convince that since this is Newtonian mechanic, so I could not avoid showing this here. This is Newtonian mechanic. All the trajectories between the fragments, given their size, the number of elements they bear, can be completely described. So that's also the interest of this kind of experiment, because you see exactly what you want to understand. And so this is traditional mechanics. There is an escape velocity, the escape velocity being referring precisely to the velocity of the fragments, the expanding velocity when it is large enough so that the cohesion will never bring them apart anymore. These trajectories will never collapse again. And there is, so this is the kind of Weber number. This is the reason why the Weber number has to be smaller than unity, because this quantity epsilon has to be larger than unity. When it is equal to 1, the aggregation time between two clusters becomes infinite, and this defines precisely the end of the inverse coalescent cascade. So this is the reason why this guy has to be smaller. Okay, so this is traditional mechanics. The mean fragment size corresponds, this is what I've just said, to an aggregation time which becomes infinite. This epsilon has to tend to 1, and this gives an average number of beats per cluster, which is an interesting function of the Weber number. A dependence which was somehow known from Grady from some time ago. So of course, when the impact is more severe, the end number of beats per fragment is smaller. This goes without saying. All right, to connect with what I have just said before, with aggregation criterion, you see that starting with clusters which are a little bit below the average or a little bit larger than the average, to provide 2 times the average. There are many ways to do that. You can start with a cluster which is close to 2n and add a little bit of beats, or have clusters which are comparable in size, which both of them give the same final cluster. However, that process is likely to occur much more rapidly than this one, so that this guy will not have time to, I mean, in an experiment, it would be very difficult to have sizes p in the distribution of the fragments, so that the criterion for aggregation, again, is that this coalescent time should be smaller than the mean-field coalescent time corresponding to this scenario. And if you plug this in with the gamma distribution, and given the mechanical description of the coalescence time between two clusters of size p and q, you end up with nu equal 8. And consistently, nu equal 8 is also equivalent to the critical size, so critical size, which I called p previously, smaller than, it cannot exist if it is smaller than 0.27 the mean, and indeed in the experiments, no fragments at any time could be detected smaller than 0.25 the mean, because they had been coalesced too rapidly. So this is a double consistency. The order of the gamma distribution is indeed the one which is expected, but also the critical size below which no fragments could be detected is well represented. Okay, so that was a variation in some sense on the previous thing. So we had been annoyed for ourselves, but by people examining our work too, by the fact that the forces, when they have a magnetic origin, never end. I mean, it's a long-range interaction. And people were saying, oh, okay, that's true, but that's interesting. Well, some were saying that's not interesting. But in real solids, or in the real world, the interaction between particles it has a finite range. The covalent bond has a finite range. Van der Waals forces have a finite range. So if you want to do something which is relevant to the real world, you should incorporate this ingredient. So this is what we did. Using gel beads. So this is essentially water in a matrix of polymers, and since this is essentially water, it is easily wettable. so that the beads can be linked by liquid bridges.
What is outside what is the polymer outside? That the whole surface outside the droplets is polymer?
And the inside as well.
And the inside?
It's a ball of polymer which can absorb huge quantities of water. So initially you get them as beads like this. This is 1 centimeter or something like that. No, 5 millimeters. So it absorbs water, it inflates, and since they were prepared in the inflated regime using a capillary instability to form them, this is how they constructed them, they manufactured them. They're practically very nice spheres. So they obtain these spheres, they dry them, they sell them, and we reinflate them by
Fantastic.
putting some water in. Okay, so the trick to self-assemble this this assembly of beads is to use a soap bubble. So surface tension is here to helps at putting this on a rounded frame. And again, we expand them. So this is an extremely fragile object. The cohesion forces are by surface tension only. So there is a trick to expand them using an elastic sheet, as you can see. And this is seen from above. So the interesting location here, for instance, you see that these two guys wanted to escape, but they will remember that surface tension is weak, yes, but not but strong enough to pull them and to so that the phenomenology is relatively identical. Of course, the range of the force is the range is the distance below which the liquid bridge breaks. Of course, as soon as it has broken, the object can see them. But the rearrangements occur as long as the bridge is present. Okay, so not surprisingly, the distributions are relatively well represented by the expected gamma. The order is broader, not because it is the force has a finite range, but because there is a noise in the bond strength. Indeed, as you have seen, the initial shock reorganizes the liquid along because the necklace has to extract itself from a deformable plate. So that's, and the bonds are not all equivalent. So there are bonds which are strong and some others are weaker. So the inverse cascade is interrupted earlier, giving rise to a broader distribution because of this noise. All right, I have no time, but I could describe the continuous fluid version of this problem, studying a bubble, an envelope of liquid, which is suddenly expanded, and we would see the same kind of interaction and the same kind of coarsening process giving rise to fragments in the end. But based on the two examples I have described, I would like, in the Newton style, finish with a scolium. I have presented two instances of fragmentation in some sense, starting with a big object and ending with smaller objects. This is at least how you have been taught at school. This is not what we've seen. In two situations we've first seen the formation of very small fragments, and from the interaction between the fragments, we have seen the formation of larger objects, so that fragmentation is an aggregation process rather than a sequential cascade of breakups. This is the truth. I see that you're disappointed. So I would like to now finish to to give a last example, which is exactly at the opposite of what I have just said, in order to reassure you. An example involving a direct process from a fragmentation process from big sizes to smaller sizes. So at the opposite of what I have just shown.
We do talk about the inverse cascade in some contexts.
Absolutely, in 2D turbulence, for instance.
Exactly, yeah.
Yeah, so that's very similar. So I was about to allude to this precisely. I will not be talking about the inverse cascade in 2D turbulence, but this is a little bit similar. I will be talking about fireworks. So fireworks, as you know, they are very popular in Japan. They were developed 400 years ago during the Edo period. And there is a cult for fireworks in Japan. And if you look precisely at what is going on in a firework, you see that this so-called mother drop, and I will explain what mother drop is, ejects droplets which themselves serve as mothers for the ejection of other droplets, and so on to viscosity, and so on to dissipation, representing a direct cascade in the usual sense. So this is a movie showing the mother drop. As you see, it is jiggling. The reason is that it is composed of carbon, and sulfur, essentially. Carbon, when it is heated, reacts with the oxygen of air in a very violent, reaction, which heats the liquid, which go on heating the liquid, sustaining the temperature, the high temperature in the droplet. And since there are other products, notably potassium nitrate, which are easily decomposed at high temperature, this overall mixture produces decomposition gases, and this is the nucleation of bubbles inside these droplets, like we see in the mother droplet. All these black holes you see are pockets of gases which break at the surface of the mother drop, therefore ejecting a jet. This is how the droplets are, the secondary droplets are formed. But in a fractal way, that guy, when it has sufficiently reacted with the oxygen of air, will be hot enough to initiate decomposition reactions inside of it, a pocket of gas which will burst at the surface of the droplet, and therefore ejecting a new droplet. So this is how the cascade proceeds. And we see that the traditional phenomenology of fragmentation, so the cavity has burst there, the liquid shapes into a kind of ligament. This ligament breaks into smaller droplets, so this is very similar to what we've seen at the edge of a stellar sheet. And as long as the droplets are not small enough so that the chemical heat release is not counterbalanced by diffusive cooling, this cascade proceeds. And we were able to see up to 8 cascade steps representing a very substantial size reduction from the initial size of the mother bubble or mother droplet to the final products. So with this conventional fragmentation cascade, I will stop.
Thank you, Emmanuel, for this beautiful talk.
Yeah, so I had promised to allude to turbulence. Right? The big difference between this process and the others I have shown is that this process is sustained at each step of the cascade because of the chemical reaction with the ambient air. So energy, in some sense, the energy which is necessary for fragmentation is provided at each step of the cascade. In the other examples I've shown, the mechanical energy is introduced in the system from the start, and it's just a coarsening process with a fixed amount of energy which was provided initially. And this is the reason why the inverse cascade. That's obvious.
Do you know any relation between the mother droplet and the small droplet size compared to that? You say the 8th generation, but
Yeah, 8th generation.
Do you know any relation between the mother one to
Yeah.
It's some
Yes.
similarity.
Yes,
between one generation.
This is documented. I mean, we've documented this. Now you have to compute the way it goes is that you have a droplet with carbon, sulfur, etc. Okay, this is the liquid. Now oxygen of air diffuses inside the liquid, where it is consumed extremely fast by a reaction with carbon. There is thus a skin, a flame front in some sense, a skin where the reaction occurs. Its thickness is square root of D, diffusion coefficient of oxygen in the liquid, divided by K, the constant of reaction. That guy is extremely large, the reaction is extremely fast, so that the heat release is made practically at the surface of the droplet. Okay? Now, the heat diffuses inside the liquid. It is produced at the surface of the droplet, as I have just said, and it diffuses inside the droplet. And this is the limiting time, which sets the time you have to wait from one step of the cascade to the other. The time it takes for every droplet, for a droplet to heat. Now, when it is hot enough, when its temperature is high enough, there are decomposition reactions which occur in the liquid, nucleating gas pockets at random. And these gas pockets, as they grow, they will at some point reach the surface and burst, emitting a jet. You are familiar with this, right? So you have the ratio, the typical size of the ejected droplet depends on the location where the nucleation pocket has been made, and it is easy to compute, given the probability. I mean, you can describe this. I mean, it's very very easily describable. You can even describe the distribution of droplet sizes which are emitted. We've documented that.
The shape of the mother droplet is quite remarkable. Have you given it a thought?
What is remarkable is the way they do that. They're using paper in which they put the so-called black powder. This powder, because of carbon, is black. So they put a layer, a thin layer of this powder in the paper, and they twist the paper by hand. It's a work in itself. I mean, it's a job in itself to do that. You would not succeed. I'm sure you would not succeed. This is extremely difficult. And what you see. So the yellow thing is the paper, and the drop hangs there because essentially it is there is a kind of an envelope, if you like. The powder is there, and it is melting here, but it's not exactly that because it is covering the paper. So this is the reason why it has this strange shape that has more to do with the shape of a droplet on a fiber, for instance. It's the shape of a droplet on a fiber.
What about the tip, the conical It seems conical.
Yeah, it seems good. There are probably solid particles.
Hanging.
Yeah, hanging. So it's, the geometry is not that simple.
So can you determine the maximum value there without fitting parameters in this kind of probability density functions?
Yeah, yeah.
Like,
You mean the maximal
like
extension?
in your universal probability density function,
Mm.
you have to stretch the y-axis as well, right? You stretch it based on the maximum at each particular time. For example, in your second example.
Ah, yeah, we're
So
not
it's
talking
one
about
way.
this anymore. Okay.
Yeah,
Okay. Stretch.
you have to stretch the y-axis as well. But can you go to two slides before?
Two slides.
Yeah. If I recall.
No.
Now it's the beads problem.
Ah, the beats
Magnetic
problem.
problem.
Okay. Oh yeah, yeah.
That one is.
No, what I am. Yeah. You have to stretch everything. I
Yeah.
mean, it's just a direct histogram what I am showing. Yeah.
It's the next on the right. You have to stretch the y-axis as well.
Yeah, sure.
So
So
how
you
do
have to
stretch
multiply.
that?
You divide. When you divide this by the average, you need to multiply this by the average. So the integral is still wrong.
Well, I guess my question is that as time progresses, you have different maximum values over there. Right?
Yes.
So what determines this maximum value?
The maximum is proportional to the mean in a gamma distribution. There is a little shift between the maximum and the mean, which depends on the order.
So there's no feeding parameter.
Well, the only so from this experimental distribution to this, it's only there is only the rescaling I am described. There is no fit at this point.
The
Now,
blue line is a fit.
If you decide the fit is the blue dashed line, if you decide to see a gamma distribution there, then you are left with one order to fit, and this is the new equal one. But the experimental processing of the distribution involves no fit.
John?
I'd like to ask something which is not quite in the spirit, but maybe you've thought about it. We've been looking at swarms of krill and thinking about animals swimming together in the water. Or possibly we've been looking at the Tour de France, where people are.
I try to avoid this.
where there's a lot of togetherness, and then all of a sudden things fall apart. So there's and presumably it's visual in the Tour de France. It's a wind drag and all of that sort of thing. Have you looked at all at sort of individuals making clusters and then falling apart all of a sudden?
No.
Okay.
No.
I have a feeling that there's some possible relation to that. Okay. All right.
At the Tour de France, in my recollection, the bottom line is to be the first online.
No, I don't think so. That's not the.
At the end, when you finish, you're
Wait,
the
wait,
first.
Only at the end. If you've been,
Oh yeah, because you're shielded from the wind.
Exactly.
Right?
And so,
okay.
so then all of a sudden,
Okay, yeah.
it all changes.
Okay.
All right, never mind.
I have a question. I'm a little confused as to the universality of these processes. For example, suppose instead of magnetic that goes like 1/distance force, you have Coulombic-like interactions with 1/square.
Mm.
How different your results would have been?
We have been trying with different. I think they will not be different. That was also the purpose of the finite range, which is completely different.
Correct. Completely different.
And the in between the contact and the position where the bridge breaks, essentially the force decays exponentially with the distance. So that's a way to play with the force. We would have liked to use to make Coulombic interactions using charged particles. We have the beginning of an experiment on that, but I'm not showing anything. So, but I don't expect any change. I mean, I don't just in the overall phenomenon, it will be exactly the same. Of course, the order of the gamma distribution or things like that might change because they will depend on the detailed microscopic. But what matters is the hierarchy of time scales.
In that case, it would be nice to have a more general description of what are the necessary ingredients for this kind of behavior.
Yeah, the aggregation enforced or induced by cohesion.
But all your examples, I think, had inertia being the thing that breaks up the cohesion. What if you're on a much smaller scale and it's friction or viscosity dominated?
The bottom line is to describe the hierarchy of aggregation times. If friction is a relevant ingredient, it will set the value of the aggregation times. That will not change, I think, the overall behavior. The fact that the distribution will have the form I have, the shape I have described. But the order will be different, most probably, because it will depend on the microscopic interaction in the sense of the hierarchy of time scales, which now will, in the example you have in mind, at small scale, will depend on viscosity.
Jacques?
For the water bells, have you tried to change the viscosity or make it viscoelastic to see if that?
So viscoelastic, we have not done that, but somebody in Paris did it. There are very interesting things there. The viscosity, yes, I mean we can talk about it. Nothing. There is no. Yeah. I mean there are quantitative changes, but no qualitative in physics.
The parameter value will change, right, from 4 to 8, whatever.
Could you do your magnetic experiment on a surface instead of a line?
Yeah. We've done that.
You have done that.
Yeah. So
Can you show us?
You have instead of a line. What?
Can you show us?
No. I'm not prepared to make it.
Great. Any other questions or comments? If not, let's thank Emmanuel.